yeah, thanks for the segue, Cheng. It's definitely, you can definitely see that AI can quickly become a problem that depends on hardware performance, and that eventually leads to what we would call HPC, high performance computing. Many people experience this with capability to use some GPUs. You can get access to some TPUs and Colab notebooks. You can get access to GPUs and experience a little bit of this for yourself. But for me, coming from Hewlett Packard Enterprise, where I work, the the relationship between AI and high performance computing means that organizations as a whole are trying to build big clusters to support people building lots and lots of different models to support many different types of applications, like George just showed, many different types of models for a single application to test what's going to perform the best, and just generally support some sort of a software development lifecycle for AI, which ends up being very different. So I've got some slides to talk about what we would call novel processor architectures, which just means evolving beyond the CPU and in some cases the typical GPU, and how you might go about thinking about that. I'm going to start by talking about why accelerators in the first place. It's important to understand that accelerators don't just mean GPUs or general purpose GPUs, as the GPUs have been adapted over time. There's many other types of processors that can accelerate the computation, whether that's for training neural networks, training machine learning algorithms, running inference of either to make better predictions or improve the latency or frame rate in a given application, as we just saw from George, right? And so generally speaking, broadly, what we've seen since 2012 is that the demand for data center compute for AI has doubled every 3.4 months. So this is not just on an individual basis, if you think you need a bigger system every 3 months, but organizations who are trying to do this at a large scale end up doubling their demands every 3 months that we've seen. And you can see some of this in the chart on the right side. Computing power required is seriously accelerating over time. Another thing that's being seen is that as the problems people are trying to solve with neural networks and AI grow in complexity, the size of the models that are being used to solve those problems also grows. And this means that we're unlocking either new capabilities that models weren't able to do at all before, or improving the accuracy of a given model on a well-defined problem, or improving the ability for the model to generalize to new data, right? Even though something may perform to a certain level of accuracy on a training and a validation and even a test set of data, how does that model perform when new distributions of data are seen from applications, new behavior from users, new inputs over time? Larger models are typically able to generalize better. And again, there's a chart on the right here so that you can see that the trend is clearly that models are growing in size and in accuracy and in capability and in generalization over time, right? The third thing here to talk about is that just these models, specifically how they get implemented, is also changing over time. So just like how models have new capabilities at a larger size, those larger sizes require new capabilities from hardware. So something worth saying is that bigger models actually require not just distributed training today. If you think about some of the language models that are on the right side, moving away from video and images and into a different domain of AI for a second, you can't implement these models on a single GPU, on a single system at times, either for training or for inference. And so as models grow in size and the state of the art grows in accuracy and generalization and capability, the capability of the hardware or the software platform to train those models also needs to change. Another thing, to think about, why we might go beyond a single GPU is just that as people like those who are on this call right now improve their skill sets and start solving more and more important problems for businesses with that more and more accuracy, practitioners' time becomes more valuable than the compute costs, right? So even if it may have been okay to wait for a couple hours for a model to train in the past, well, if we're paying somebody to sit around because all of the compute is busy, that's probably not a good thing for the business, right? The last thing here is just that, the idea that only models are growing is also not true. Data sets are growing themselves. And this is in many cases what leads to better accuracy, better generalization. But we've seen that when comparing to the demand of data center compute, data storage capacities double somewhere between every 7 months, according to Gartner, and 12 months, according to Illumina. So depending on the analyst that you're thinking about here, we can generally say that about a doubling in the amount of data required for a business to run an AI project results in 5 times more compute. Right? So again, we all know about the growth of data, but what if the amount of compute that's growing is growing at 2.5 times that rate, right? Okay, so what does this actually look like in practice? Well, I think many people will be familiar with this, but I want to define that term HPC we talked about earlier before we go any further. The journey that I'll talk about here is what we would call the distributed or parallel processing journey. It may be familiar to anybody who has HPC experience, but for many people who are just starting out with AI, what happens on the GPU, on that processor, to actually make training go faster or make inference look smoother, that's not easily understood, right? So I'll just talk here about what happens on a server today. If you look at any application, not just AI, most things start as on a single machine using a single thread. Over time, people develop parallel processing techniques so that a single machine can take advantage of multiple threads, right? Anybody who's done any sort of programming is implementing this, whether they know it or not. Most people actually do know about this, though, right? Multi-threading, hyper-threading, you'll hear about these terms, and obviously write software that takes advantage of the machines that are being used and doesn't just process everything linearly. So when we think about how this grows over time, a very common experience is just to have, okay, I've got more than what a single machine can handle, a single machine's threads or a single machine's cores can handle to process a certain amount of data or whatever my application needs to do. And so I'm going to scale it out across multiple machines, right? We know all about scale out design and designing for the system, right? And in the HPC world, right, maybe not software in general, where people are developing web apps and mobile apps that are going to stand up a new container that could end up running on the same physical machine or something different, stand up a new virtual machine, whatever that is in your cloud infrastructure. In the world of HPC, a user that's using more than a single node's capacity to process some amount of data, run a simulation, do some sort of new modeling, they would be doing a multi-node job, and this is something that's common in what we would call a traditional x86 HPC cluster. People have been doing this for a long, long time. But what this requires is a really fast network, right? Because you have to have communication between all the nodes to constantly update things. If you think about an AI model training, if that model has to be distributed across multiple machines and we need to update all the weights at one time for one forward pass or one backward pass, well, I'm going to need all the nodes to communicate to each other at any one time, which means a lot of traffic on the network. So lots of bandwidth, very low latency, that's required. Alternatively, right, let's imagine that we don't care about the clock speed of a single CPU, well, and we don't want to deal with managing anything to do with a network or multiple machines. That's when we turn to a GPU. And so most people who have developed neural networks today, instead of turning to multiple machines with multiple CPUs, many threads, and worrying about parallelizing your code across many different machines, we immediately just throw a GPU at the problem and it does it for us. That's great. But in the current day, again, as those models grow in size, as those data sets grow in size, we suddenly need more than just one GPU to be happy and be productive. And eventually, we're looking at a server or a workstation that could have 4 or 8 GPUs just for one person's project, and that can get really expensive. And if everybody's got one of those things, but they only use it for certain periods of time during the day or the week, is that really the most efficient way to go about doing things? So what if we combine the two, right? What if we have multiple machines with a single GPU? This is what we would call a converged HPC or AI cluster. Many different research institutions, government entities, the Compute Canada here, they have these sorts of systems that are going to have multiple machines, each with a single GPU in it, or a few GPUs, and we're going to call that a converged HPC or AI cluster because the sort of processing that's happening on any one of those nodes, it doesn't really matter. These machines are good at doing anything you throw at it, basically. Now, if somebody's really growing beyond that workstation or that server, that's where we would call an AI cluster, right? I have a cluster of machines that CPUs aren't that busy, the memory's not that important in an efficient run. We're really just focused on the GPU, and that's the AI cluster, or something called a pod. Hopefully over this time, you can kind of understand that HPC people and AI people with different backgrounds are kind of coming together to understand the difference between a scale out and a scale up architecture. And I just want you to keep this in mind as you kind of go about your journey, right? People will start to add GPUs to a single machine until it runs out of space, and then, oh no, I don't know how to share that with other people. But if I just start doing everything in cloud infrastructure right now, well, costs can run away from me too, and who knows what to think about there. So a balance of both is required. Now, let's be precise about the name of the processing unit. Throughout this presentation, I've kind of been calling everything a GPU, or a graphics processing unit, thanks to NVIDIA. Obviously, we know that there are GPUs transcoding the images and videos and whatever other multimedia is being put on screens every day, so we can have this conversation, right? But when we think about GPUs that you might use for training a neural network, things like the T4, the V100, the A100, these are really computational accelerators, right? They're not built for graphical processing, and NVIDIA will distinguish between these two classes, calling the products a general purpose GPU, right? Which is kind of interesting. General purpose graphics processing unit. Well, general purpose graphics, it's not doing graphics. What is it really? Well, we would call it a computational accelerator. But the thing is that there's a spectrum of things available here. There's a whole bunch of different processors that can be used, and they fall on a landscape or a linear spectrum here called from flexibility to efficiency, right? On the left side, clearly we have a CPU that is the most flexible option, but it's very inefficient for things like the matrix math we need to train a neural network. On the other side, things that are very efficient, like ASICs, low power requirements to do a very well-known task, are application specific by the name, right? And so what's the spectrum in the middle actually turning into today? Well, on the left side, we've got the GPUs. We're kind of familiar with GPUs, might fall into that section as well. But somewhere in the middle, we've got this emergence of these things called an FPGA, or a DPU for deep learning processing unit, a TPU that you might get access to in a collab or something available from Google. Different vendors will put PU at the end of the name of their quote unquote chip. And so we end up with a spectrum of offerings that are available for somebody to buy, right? Today, NVIDIA is clearly the leader in this space, but we know that the future is effectively going to be heterogeneous. There's going to be a mix of different things for different purposes. Maybe I have a special training accelerator that pushes things to the CPU for inference. That's a pretty common workflow for today's development of neural networks. But what if that network goes 10x in size over the next 5 years? I'm going to now need to train across multiple GPUs and deploy to inference on a single GPU? Or what if I could get a better accelerator for training and maybe something somewhere between a GPU and a CPU for inference? That's what we need to think about when we look at some of the logos on screen here and actually make the proper assessment. But to do that, it's difficult, right? There are a whole bunch of different chips out here on the landscape. The logos I was showing on the previous screen are not exhaustive. It's not an exhaustive list, just kind of meant to be representative. And this GitHub down here, a little bit out of date at this point, but maintained by somebody that I don't know. And it's great work, right? Just the ability to summarize how many different logos there are and put them in some sort of a category right now so that you can go pull on a thread, Google something that seems interesting and find out what it is that they're up to, right? ICs and IPs, as we know here, right? And this isn't just limited to AI chips, quote unquote, right? We also have some different software technologies like compilers and different benchmarks that I'll talk about a little bit here. So, okay, so how would I actually go about distinguishing one logo from another here? And how can I do this in a methodical, more repeatable way? Well, at HPE, we go about it in what we think is a pretty unique way, right? There's many different technical factors and business factors that need to be considered when you're actually going about deciding which accelerator to buy, or just measuring the performance of two different offerings, right? Just being able to do an accurate comparison. The problem with benchmarks is that when people run them, suddenly you can now tune the accelerator and the entire environment to achieve that benchmark's measurement of like the best measurement from that benchmark, right? As we know, when a target becomes a measure, it ceases to become either, right? So benchmarks can end up serving that purpose here and not really representing what something's going to behave like in the real world. Beyond that, the complexity that it is required to get some sort of benefit over the standard can be a non-starter, right? Why would I spend more time? I've got a really difficult AI project coming up that's going to cost me a bunch of time up front, technical debt if it doesn't work. This whole thing I got to manage. What really happens if all that goes to waste, right? That whole dynamic is present when it comes to evaluating accelerators as well. And the other thing is that it's very hard to do apples to apples comparisons. Some of these accelerators have been developed for such unique purposes that they functionally can't do certain things, and on a performance perspective are incredibly performant for other things. So we, to compare things apples to apples or do some sort of TCO, total cost of ownership analysis about what to buy, what to use, what to spend time researching, it's really, really difficult here. So this is just an overview of kind of the different things that we take into account during our evaluations. And there's also a link to a paper down below that's available publicly so that you can read about some of the findings that our team did after going through this evaluation for a few different vendors. But okay, let me talk about this process. I think that it might be a little bit interesting for the audience here to know about, just because when you're getting started with a framework like TensorFlow, or you're considering many different types of algorithms or use cases or approaches to take with an AI project, it's usually nice to know what others are up to. And one of the benefits of working for HPE is that we get to serve customers all around the world. So we get to know exactly what people really care about. And so in phase one, we did what we called a functionality test, right? Functional benchmarks, which is kind of a misnomer because benchmarks are meant to say something about performance in most cases. But in this case, it was just meant to say something about functionality, right? And so you can see, I'll go through the models one by one here. You can see different types of models, different types of data sets, and then the reasoning why it was selected in this functional thing. In this slide, there's links available. So if we distribute the deck, or if you take a screenshot and you Google some of these things, maybe you'll be able to see why they were selected for this purpose, and hopefully understand that this is representative of a lot of different use cases across many different customers. So, one by one going through here, Higgs Boson is a great model. The data sets from the UC Irvine machine learning repository, which in and of itself is a great resource for anybody who wants access to really, really big data sets that are really good to get started on. And the reason for selecting it was to understand the portability experience, right? If Higgs Boson runs on something else, what does it take to actually just port this model to the given accelerator that we're working on here? The next model is ResNet 50. ResNet's a classical CNN. Hopefully everybody's familiar with the concept of a CNN here, and also familiar with the ImageNet dataset. So there's hopefully no questions why this one shows up. We see a lot of ImageNet and a lot of ResNets from many, many different customers. Anybody with image data has probably worked with ResNet 50 or other ResNets. RNNs are also very popular, right? Two most popular types of data. We're talking about images and we're talking about text. In this case, the char RNN model was tested to demonstrate whether that accelerator actually had the availability of a sigmoid kernel, and whether we could actually use that, because it's very popular in many, many networks out there. The third one, fourth one, based on customer popularity, is BERT. Anybody trying to do natural language processing or who hasn't heard about transformers from Google, definitely give BERT a look at. It's been transformative, pardon the pun. The fifth one here is StyleGAN. Generative networks are really interesting, and the reasoning why here is to understand that a higher resolution input will change the characteristics of how the accelerator handles data coming from the machine, which is really important, right? We see a lot of people talk about how many cores, or how much processing power, how fast the clock is, how much power is required. That is one side of the equation, right? How fast my processor can go. The other side is how fast I can give it data, right? If I've got a great engine but no gas for the car, it's not going anywhere. And so these higher resolution inputs allow us to really stress the memory and the storage subsystems that are actually feeding data to the networks. The other three here are a little bit more specific in the reason why they were chosen here. The dataset CFAR10 is obviously very popular, and autoencoder models are popular as well. Or the autoencoder model is popular. VAE type models are popular as well. And clearly there is a probability constraint over CNNs to be explored here. I'm actually looking at the time right now, so I'm going to skip forward to the next slide here just to show that the phase two of the benchmark effort here, right? So when you think about phase one being a functional test, phase two turns into a performance test. And there's a lot of names of models on here. They're categorized in a slightly different way. I would say in order of priority, many people start with computer vision, start to go to NLP because of business reasons, if you're working for a corporation, and then explore other data types and model categories like recommendation systems, time series prediction, and different scientific data shapes if you're coming from an HPC background. And so the consideration here is really just to say that if there's a benchmarking effort going and you're trying to measure the performance of a given accelerator, certainly we want to show what that performance looks like across many, many different types of models, not just 10 runs of the same thing and optimizing for that very, very one thing. Because as we know, even in just building one application end to end, there could be many different models in use, many different models tried for a single use. And that's important to think about when you're testing which accelerator to pick. Okay, I think that kind of wraps it up from me. If there's key takeaways or key next steps here beyond just the accelerator, I'd encourage everybody to check out this this concept of machine learning production readiness. This is a free lecture available from I think it's called Full Stack Deep Learning. Is just a free resource that's available from a couple of people who came from UC Berkeley, I believe, and this screenshot is just their summary of a paper that was written by Google, a follow-up to an assessment of the technical debt related to machine learning. Because, again, thinking this through, understanding how to think about picking an accelerator, testing many different models, planning for growth in data and growth in models is something that should be considered at the beginning of starting a machine learning project at enterprise scale. And so I hope that these, the things that I talked about today are interesting, and I hope that you've gotten a few pointers to future stuff to look into. If anybody's got questions about hardware for AI or benchmarks or just getting the best performance out of an AI system, my email is on screen. I work for HPE. I know Chang and the organizers here as well, so feel free to get in touch, connect with me on LinkedIn.